Welcome back. Today we'll look at paper 13 of the May-June 2024 series. Now, as always, the mark scheme has been released already, so I would recommend checking that as well. However, this video is mainly for people that want extra explanation, because maybe they look at the mark scheme, they don't understand something. They want to go over a few topics again. Alright, now as always, this video will be quite long, so I'd recommend watching at 1.25 or even 1.5 times the speed. Right, question 1 says the size of a file can be measured in different units. State how many bits there are in a byte. Okay, so this one's hopefully not too difficult, right? Just about 8 bits in a byte. Right, then we want to state how many kibibytes, so KIB, there are in 2 mebibytes. So let's think, if we have 1 mebibyte, then we say that 1024 kibibytes, right? So KIB, I guess maybe make it a big K. Right, that's going to be equal to 1 mebibyte. Therefore, of course, if we want 2, well, that's going to be 2048. Okay, just multiply it by 2. Right, then we want to identify the unit of data that is equal to 4 bits. So this should just be a nibble. And yeah, I mean, this one is probably a bit tricky. Some people might not know this, but the way I remember it is, well, obviously a bit is going to be, well, just 1 bit. 4 bits is then going to be a nibble. And of course, 8 bits is then going to be a byte. And the way you can remember this, if you think about like sort of eating food, where you say, I don't know, maybe the mouse nibbled on some cheese, because the mouse is small, right? It's going to have a small bite. Whereas you say kind of the lion had a bite of the human, because obviously, well, the lion is big, right? Therefore, it's going to have a big bite. So yeah, that's how you remember. A nibble is just a small bite, basically. Or yeah, in particular, kind of half a bite. Right, question 2. An image has a 16-bit color depth and a resolution of, well, 1000 by 1750 pixels. Right, state what is meant by 16-bit color depth. Right, okay, I mean, so the color depth you can also call the bit depth as well, right there. I mean, it's the same thing. So what this is then, this is going to be the number of bits per pixel. Right, or you can also say, the number of bits to represent each color. So let's just say that, right, the number of bits. Right, the number of bits used to represent or let's say, yeah, each color. Yeah, I mean, so we could say, I don't know, yeah, each color, or we could say, to represent the color for 1 pixel. They would be equivalent explanations. Right, then we want to, well, the resolution of the image is changed to 750 by 1500. Give the effect this will have on the file size of the image. Right, I mean, so here, I just want to look, is there any relationship between 750 and 1000? So I guess here it's gone down by, well, obviously like 1/4. But 1750 by 1500, right, is well, it's not going to be a quarter, right? It's obviously a different ratio. Because, for example, let's say they had an image that went from like 1000 by 1000, let's say it went to 500 by 500. Here they might be looking for us to specifically say, like the actual kind of amount the file size reduced by. And obviously here you have to be a bit careful, because some people might think, oh, well, it's just, divided by 2. But in reality, well, because the width is divided by 2, also the height is also divided by 2, then of course, well, the total effect is actually divided by 4. But yeah, I think, between these two values here, there's not really any relation. So let's just give a general, let's just say, yeah, the file size will decrease. I think it's more like the physics papers where they want a specific amount. You say it kind of increases by 2, it decreases by 3. Yeah, I guess the computer science papers, they don't really want you to be that specific. Right, 3. A program is creating a computer game. One character is not moving correctly. The program needs to debug the program. Right, to do this, they need to look at addresses that are locations in memory. The addresses are displayed as hexadecimal numbers. One address is A to F, and we want to convert the address to binary. Right, I mean, so this might look, quite intimidating first if you think, well, what's this in hexadecimal? But if you just remember that to convert from hexadecimal to binary, we just have to remember that 1 hexadecimal sort of digit or character, right, is going to be 4 bits. So A is obviously going to be 10, and to represent 10 in binary, well, that's just going to be this, right, 8 plus 2. Right, then we go on to the next character, this 2, and of course, well, let's go, what, 0, 0, 1, 0. Which of course is 2 in binary, and then what, F, right, that's quite easy because that's just all 1s, right, F is 15. Right, then this is actually harder, even though this is only worth 1 mark, this one is worth 3. But we want to convert the address to denary. So I mean, I guess you could actually just use this binary and convert this binary to denary if you want, or it's probably better to use the original, because I mean, let's say here if you've made a mistake, well then of course if this is made a mistake, you're going to be just copying the wrong mistake again. So yeah, let's use the original. So what we want to write out the hexadecimal positional value. So 16 to the power of 0 is going to be 1, right? 16 to the power of 1 is going to be 16, and 16 to the power of 2, right? That's going to be 256. So what we want to think, well, we've got a times 256, so that's just going to be, 10, right? So 10 times 256 is just, 2,560. Then we've got two 16s. Right, so obviously that's going to be 32, and then we've got f, which is just 15. And I guess if you want, right, so here it doesn't say show all of your working, so I guess we don't actually have to show everything, but of course if we wanted to do it properly, of course we can just add it like this. So that's going to be 7, 6 plus 3, right, that's going to be 0. So I guess this is hopefully our answer. If I've not made any mistakes. Right, the binary number stored for another address is this. Convert this binary number to hexadecimal. And again, like we said, one hexadecimal character is 4 bits. So we just want to convert this into 4-bit nibbles basically. So yeah, maybe I'll just draw lines like this. Okay, there we go. Right, so the first 4 bits we can see that's just going to be 1. Right, the next 4 bits, well, that's going to be 9 because we've got 8 and a 1. So yeah, 9, and then the next one, that's 8 plus 2, that's 10, right, plus 1, that's 11. So 11 in hexadecimal is going to be B. And of course, the way you remember that, A is going to be 10, right, therefore B is 11, C is 12, right, etc. And of course, your F is then going to be 15. Right, then we just want to convert this number to denary. Okay, so this one's a little harder because, well, again, I mean, obviously we're going up to 256. I mean, so if we want, well, let's just write this because, I mean, this 1 is going to be 256. Right, so let's go 256. Right, we've also got a 128. Right, then we've got no 64, no 32, but then we do have a 16. Alright, we do have an 8. And then, we do have, a 2 and a 1. Alright, so, 6 plus 8, that's going to be 14 plus 6, alright, 20. 28, 30, 31. Right, so that's going to be 1, then we carry a 3. Right, then 3 plus 5 is going to be 8, plus 2, that's 10, right, plus 1, that's 11, and then carry the 1, and then here, that's just going to be 4. So I think that should be 411. Again, I'm just going to double check that, so 256 plus 128. I mean, hopefully this is right. If there's a mistake, I guess I'll go back and change it later. But yeah, hopefully that's right. Okay. Right, so then we want to give one reason why the addresses are displayed in hexadecimal instead of binary. And I think for this, what we can say is obviously, hexadecimal, you say it's going to be easier for a human to understand, right? Also, it's going to use up less space on the screen. And if you say this, if you give this, less space argument, you have to specifically say, right, on screen, because otherwise it's ambiguous. Maybe they think you mean less space in memory, right, which is obviously not going to be true. Because, I mean, in reality, actually, of course, they're all stored in binary in memory anyway. But let's just go with the easier for humans to understand. Right, let's say, easier for humans. Right, I'm just going to use shorthand, right, to understand. And let's say because, maybe because it's sort of shorter on screen. Right, and I guess because it also, uses more I don't know, maybe and uses, I don't know, more than 2 different characters or something. I think this explanation is a bit sort of unnecessary. We can just say easier to understand. It should be fine. Right, then we want to identify 2 other ways that hexadecimal is used in computer science. Right, so I mean, let's try and list maybe 4 or 5. So one is going to be IP version 6. We can also think MAC addresses. We can also say, well, color codes, but I think specifically I did check the mark scheme, and they say you have to actually say HTML color codes. Yeah, just saying color codes is not enough, right? You do need HTML, right? And then, I mean, what have they said here? Okay, right, so yeah, here they've already said memory addresses. So others you can give, I guess, error codes. Yeah, I think they would be the main ones, really. Right, so the health value for a character in the computer game can sometimes be a negative value. The negative values are stored as 2's complement 8-bit integers. Right, character has a health of -25. Give the 2's complement 8-bit integer for -25. Right, and yeah, this time we do need to show all of our working. Right, so here then again, let's just write out the positional values. So -100. And I mean, okay, so this one, there's actually a few different ways we can do it, and I guess I'll show both ways. So we can just directly calculate like this, right? So -128, 64, 32, right? 16, 8, 4, 2, and then 1. So you think, well, because it's minus, of course, we need the -128, right? Then we also need to plus 64. Okay, this will get us to -64. Then if we plus 32, right, this will get us to -32. Right, then if we, well, I guess we don't want to plus 16. Also, if we plus 8, this is also too big. So right, if we plus 8, that gets us to -24. Whereas, of course, yeah, we want to be -25. Right, so if we plus 4, this goes from -32 to -28. Right, plus 2 gets to -26, and then, yeah, plus 1. Right, that's going to be -25. And, you know, I guess since it says show all of your working, I mean, you can probably do this, yeah, I don't know, or like, you know, -28 plus 64 plus 32. And I guess just write that equals -25. Right, the alternative way to do it is, well, you can calculate the positive 25. So let's say yeah, I don't know, I mean, I think I won't do it again because it's going to be sort of too long, or yeah, not enough space. But positive 25, well, there's no 128s, there's no 64s, there's no 32s. Right, there will be a 16, I guess there will be an 8. Yeah, no 4s, no 2s, and then there will be a 1. Yeah, that should be fine. Right, so again, right, this is positive 25. Then to convert this to negative 25, well, there's 2 steps. First, we want to flip the bits, right, or invert the bits. Okay, then we want to add 1. So flipping the bits, well, 0 becomes 1, 1 becomes 0. Just like that. Okay, right, then we want to add 1 to this. And actually this one, because this last digit is a 0, or well, because this last bit is a 0, then we should be able to see that actually, right, you know, this 0 is just going to change to a 1. But of course, since it says, you know, show all of your working, yeah, I guess you would want to do that, and then of course, well, just, yeah, write the final sum here, which I guess if we start from right to left, well, 0 plus 1 is going to be 1, right? 1 plus, okay, sorry, right, 1 plus 0 is 1, right, 1 plus 0, that's 1, 0 plus 0 is 0, right, 1 plus 0, and yeah, of course, so this should be our final answer, and of course we can check, so this answer here is going to be the same as this one. Right, for the table contains statements about types of secondary storage. Complete the table by writing the correct type of secondary storage for each statement. Right, so this one I was a bit confused because I was thinking, like, do they want us to list the general terms? And if you remember, the general terms, there's going to be 3. There's going to be optical. Right, there's also going to be magnetic. And then finally, there's going to be solid state. So yeah, I was thinking, well, does it want us to list these general terms, or does it want us to list, you know, specific, like CD, yeah, hard drive, you know, say SSD. But yeah, I think when it says type, then here they're really talking about the general type. So when it says pits and lands are created on a reflective surface, well, this is talking like CD, DVD, Blu-ray, right? So this is going to be optical. And well, again, you know, just to recap how this works, so pits and lands. That's saying you have a sort of pit and a land like this, which, yeah, these are kind of like, well, these are, you know, sort of burnt into the CD or out of manufacture. And then, well, you're going to have a laser, and then the laser will shine this. Now, if it hits a pit, right, this laser will then get reflected. Whereas if the okay, sorry, right, yeah, this is going to be a land, right? If a laser hits the land, it will get reflected. Whereas if the laser hits the pit, right down here, right, then it won't get reflected. And of course, yeah, this difference between, well, reflected or not reflected can correspond either to, you know, say a 1 or a 0. Yeah, that's how that's going to work. Right, the next one, well, NAND or NOR technology is going to be used, so that's going to be solid state. And I mean, when it says NAND, well, that just means, you know, like the NAND and NOR logic gates. Right, then platters are spun that are divided into tracks and sectors. Right, so that's going to be magnetic. And in particular, when it's talking about a platter, well, a platter is the disk, right? So this is going to be a hard drive. And of course, you know, again, a hard drive is going to be a disk like this, right? That's the platter. I mean, the tracks, right? That's going to be, you can kind of think like each, let's say like each different radius would be a track. So, you know, this would be one track. I guess, yeah, this here will be another track like this. And then the sectors, that will be, well, you can think of a sector as like part of a track. So yeah, that's just going to be sort of, yeah, I guess part of a track really. Yeah, and of course, well, with this, you're also going to have a read and write head. Okay, so you're going to have the magnetic read and write head, which is going to, I think it's going to measure the polarity of the magnet. So whether the magnet is like north, or yeah, whether it's magnetized, or yeah, I'm not sure exactly. But I guess you say, well, it's just going to sort of measure, you know, take a sort of, I don't know, magnetism reading or something. Yeah, and well, again, I think it's going to be the polarity, right? And of course, again, that will correspond to a 0 or 1. So, I mean, actually, this one is then just the same, right? Because this is talking about the read and write head. Right, transistors are used for as control gates and floating gates. So again, that's going to be solid state. Right, I'm just going to do an arrow. I don't want to write it again. And I think, like we said in the other video, a floating gate, well, this is going to be the thing that actually stores the charge. So this will store, you know, let's say electrons, or obviously negative charge. And then the control gate, this can be used in order to remove the charge from the floating gate. Because let's say if the floating gate is negatively charged, I don't know, maybe that corresponds to a 1. I mean, of course, it could be a 0, it just depends on the hardware. But I mean, let's say for our example, where negative like means 1. Now, if we want to remove that charge, what we would then do is we would then negatively charge the control gate. And if we negatively charge the control gate, well, of course, you know, negative and negative are going to repel. So basically, this negative charge will then repel these sort of negative charge from the floating gate. And then it means that, you know, this negative charge here will then be attracted into this oxide layer. So effectively, you know, this negative charge will disappear. And then, you know, if we have, say, a neutral charge, right, that can then represent 0. So yeah, I mean, that's how that's going to work. Right, then we have a red or blue laser is used to read and write data. So if we're talking about a laser, like we said, you know, that's going to be optical storage here, right, with the pits and lands. And I mean, there is actually a slight difference. Okay, now, a pit and land, this is going to be if it's read only. Because effectively, you know, once we've like written the pit, right, I mean, we've literally burnt away some of the actual coating, right? We've burnt away some of the CD. So there's no way to go from a pit back to a land, because, you know, we can't get that physical material back. Now, if you want, say, a CD, DVD, Blu-ray that's both read and write, then it's actually going to use, I guess, some special like chemical coating. And the way that works is like you're going to have a laser, and then depending on the intensity of the laser, that will basically affect the sort of atomic properties, right, or the atomic structure, yeah, of this chemical coating. And I think, I don't know, maybe if you have a high, let's say like a high intensity laser, or yeah, maybe low intensity, that will create it where, I don't know, you have the atoms that are in this nice, yeah, let's say like a nice kind of like grid. Yeah, I think, yeah, I think, I don't know, is it like lattice they call it? I was trying to think in chemistry. So if you have this lattice structure, okay, this one is going to be shiny. Whereas if you have this kind of like random structure, I don't know, maybe one here, one here, one here, then obviously this is going to be not shiny. And depending on, you know, the sort of arrangement of the atoms, yeah, then obviously, well, shiny or not shiny, again, it's going to correspond either to a 1, right, or a 0 like this. So this is if you want both read and write. Whereas, yeah, this pits and lands, this is if you want, you know, read only. Right, anyway, number 5, a computer uses both random access memory RAM and read-only memory ROM. Right, tick one box to show which statement is correct about RAM. Right, so RAM is non-volatile storage. I mean, this is going to be false because, well, RAM is volatile. And what volatile means is when you turn off the power, right, the data is going to be lost. So yeah, this is going to be false. Right, RAM stores the bootloader. Again, that's false because, well, the bootloader is going to be stored in ROM. And the bootloader, just to recap, that's going to be the thing that, well, when you turn on the computer, the bootloader will load the operating system from, secondary storage, and it will load it into RAM. Because in order to actually, use the operating system, well, the operating system has to be loaded into RAM, right? Yeah, loaded into, primary memory, right, which is RAM. Right, stores the data that's currently in use. Okay, so this is true, because, well, RAM is going to store the data and programs or processes that are currently in use. Right, it's not directly accessible by the CPU. Well, of course, yeah, this is false because, well, RAM is primary memory, right? Therefore, it is directly accessible. And of course, yeah, here it says, tick only one box. Right, then it says ROM is a type of primary storage. State the characteristic of ROM that makes it a type of primary storage. Right, so as mentioned, let's say, well, I guess we don't really need to say primary storage. I mean, let's just say, yeah, it. Right, so it can be, or maybe, yeah, it is. And we're going to say, well, maybe directly accessible by the CPU. Okay, right, yeah, by the CPU. Because, I mean, just to draw this again, right, so here we have the CPU, let's say, okay, right, here we have primary memory or primary storage. Again, remember, primary storage has two, right, so RAM and ROM. Right, then here we have, well, secondary storage. So in order to load something from secondary storage, well, first it has to be loaded into the primary, well, let's say primary memory, right, which is going to be RAM in this case. And then, from RAM, then it can go to the CPU. So yeah, that's what it's saying when we say, primary memory or primary storage, right, can be directly accessed by the CPU. Whereas, of course, secondary storage can't, okay, because, well, we have to go to the primary first. And likewise, if we're also writing data, well, first we would write data to the, well, RAM, then, yeah, from the RAM, right, then it's going to go to the secondary storage. Next, it says a sensor is an input device that is used to capture data from its surrounding environment, and we want to circle 3 other input devices. Right, okay, so obviously a touchscreen, that is going to be an input, because, yeah, it's going to, input the sort of coordinates of the touch. And I think, remember that touchscreen, there's actually 2 types, right? There's going to be resistive, and then also capacitive. I think now for IG, they don't really need you to know the difference between these. So yeah, hopefully they won't ask about this now. Right, obviously we've got hard disk drive, I mean, that's going to be storage. Right, headphones, I mean, that's going to be output. Right, speaker, again, that's going to be output. Right, so microphone, of course, that's going to be input, right, inputting sound. Right, actuator, I mean, that's also output, because it's going to take an input signal, saying to move. And then, yeah, the output is going to be the actual movement or the rotation, or whatever. Of course, well, USB drive, again, that's going to be storage, right, printer. Yeah, so printer, this will also be output. Okay, sorry, right, we want input. Yeah, okay, so printer is going to be output. And then, of course, keyboard is going to be the input device. Right, sensors can be used in an automated system. Give 2 benefits of using sensors in this type of system. Okay, so I think we can say, obviously, a human doesn't have to be involved. So, yeah, I mean, that's kind of in the name of saying automated. So, I mean, maybe they would accept that, maybe not. Right, I mean, I think I'm going to say that, let's say, yeah, human, I don't know, yeah, doesn't have to be involved to take readings. So, I mean, this means that obviously, well, the system can operate independently. And if you think, well, if it's a monitoring system, then it's just going to monitor, right? It's just going to record. I guess, yeah, you say it's just going to record its environment. However, if it's a control system, then of course, where it's going to use the actual, I guess we can say, yeah, it's going to use those sensor readings in, let's say, in order to actually modify the environment. And then, yeah, based on the feedback, well, then it can realize, was that modification successful, or does it need to modify more or less? So, for example, let's say let's say it's monitoring the temperature. Then the control, in order to change that, I guess if it's too cold, it could be, turn on the radiator, right? If it's too hot, it could be like turn on the air conditioning. And then of course, the next stage would be the feedback, where it's then gonna, take the temperature again. And obviously, if the temperature is, say, gone towards the normal value, right, then it knows it's successful. Whereas, if the temperature is, continued sort of deviating from the norm, I guess then it needs to turn up the heater, or maybe turn up the AC, for example. Right, but then let's say another benefit. I mean, I guess you can say it's going to be more accurate. So more accurate than human readings. Also can be taken at shorter intervals than human readings, because a sensor could take, I don't know, every millisecond, every microsecond, whereas a human is not going to be able to do that. So let's just say, I don't know, maybe can take more accurate readings than humans. And I think some other advantages you could say, for example, it can work in any place. So maybe you have somewhere that's like super cold, super hot. Maybe there's some kind of toxic gas or some dangerous environment. Of course, they can also work 24/7, 365. Whereas a human is not going to be able to. And obviously, a human you'd have to pay as well. Right. So let's say more accurate readings than humans. Right, so the table contains different types of sensors and a use for each. Complete the table by giving a suitable use for each type of sensor. Right, the first one's been done. Right, so acoustic sensor to monitor whether a water pipe has cracked and is leaking and dripping onto the floor. Okay, so I think when they say acoustic, I mean, here this is probably going to be using ultrasound. Just looking for cracks in the pipe. Right, so temperature, I mean, I think for temperature you could mention greenhouse, but I think for greenhouse I'll probably, maybe this humidity, I'll mention greenhouse. So I mean, let's say temperature could be like in an office. Let's say maybe to control the temperature in an office. Let's say, right, to control the temperature. I guess, we can say, to measure. Let's say to measure the temperature in an office. And let's say, I don't know, maybe I don't know, send signals to microprocessor. Right, microprocessor. Let's say, I don't know, to turn on radiator or AC accordingly. Okay, right, radiator / AC, accordingly. Right, then humidity sensor, I guess we can say, well, to measure the humidity in a greenhouse to ensure optimal growing conditions. Right, measure humidity in greenhouse. Right, to ensure, right, then optimal growing conditions. Right, then infrared, I mean, this one is mostly, if you look at the past papers, they mostly say for movement. So, for example, like a security system. Because what you would have is, let's say you have like a room, because infrared is used to detect temperature. So, like, maybe you've seen, some security camera where like everything will be blue, right, which obviously means it's cold. And then, like in the middle, you just have like a person. And this person is going to be like glowing red because, of course, the heat from their skin and everything. So let's say that. Let's say maybe in a security system. Right, let's say to detect intruders in a building. Alright, and then this magnetic field, I mean, this is a super tricky one. I was struggling to think. I mean, first I thought like maybe it can be used for some like sort of astronomy or astronomical purposes. I don't know, like measuring the Earth's magnetic field, checking there's no sort of like anomalies. Also things like the sun, right? Because when there's a solar flare, yeah, I guess that's going to sort of shoot out like magnetic particles, or yeah, like I guess charged particles. So yeah, maybe you can mention something like that. Also measuring the magnetic field of like exoplanets, right? Other planets, or yeah, moons or something. So yeah, maybe they would accept that. However, obviously, I mean, that's over long distance, so I'm not sure if that would be a sensor or if that would be yeah, some sort of camera or some kind of other thing. So I did check the mark scheme for this, and what they say is you can use it to detect cars going in and out of a car park, because obviously I guess the bottom of a car is going to be metal. So yeah, when that passes over the magnetic field sensor, yeah, that's how they know if a car has entered or exited. So yeah, I guess we can just say that, let's say, right, cars entering or exiting a car park. But I think giving like an astronomical example should be okay as well. Right, 7, a company has a network that includes a web server. Data is transmitted across the network using serial half-duplex data transmission. Draw and annotate a diagram to show how the data is transmitted using serial half-duplex data transmission. Okay, so I think with these, before you start randomly drawing stuff, right, try to actually plan like what you're going to draw in your head. So obviously, well, one thing we want to draw is the web server. We'd also want to draw, let's say, a client or like a computer, maybe the client. Right, if we're talking serial, well, this means we want to show the data traveling, one bit at a time. And then obviously half duplex, we want to show, well, there's going to be two wires, right, two directions. But of course, it can only travel in one direction at the same time. Yeah, not both directions simultaneously. So let's try and draw that. Let's say the client. Let's say what the web server. Yeah, server, right, with an R. And let's I don't know. Let's just draw some like bits going across. And let's just say right, serial. Let's say I don't know, bits. Yeah, bits travel one by one. Right, and then yeah, I guess probably we should draw some arrows as well. Okay, yeah, that's going to be the arrow going in that direction. Right, that's the arrow in this direction. So I mean, I don't know, here let's just do some other bits. And then what we can say is, maybe let's say, right, bits, yeah, bits travel in both directions. Right, but then we want to say, yeah, but not simultaneously. Right, now, is that going to be enough? So we've got the client, yeah, I mean, we've shown serial, right, we've also shown half duplex. Yeah, so I think that should be enough for 4. Right, then we want to give 2 benefits of the company of using serial half-duplex data transmission for this purpose. Right, so I guess serial we can say, well, it's reliable because there's no skew. Or, well, okay, I mean, yeah, let's say like reliable over long distance. Right, because, yeah, there is no skew. Okay, and just to recap what skew is again, right, if we have parallel, so let's say we've got like, I don't know, 3 wires or 2 wires, I think, yeah, let's just do 2 wires. Right, so let's say we've got some bits like, I don't know, 0, something like this, and then here maybe, I don't know, maybe these. Now, if we say this wire has a relative speed of 1, but this wire has a relative speed of 1.2, and like I don't know why that would be, but yeah, maybe there's some hardware issue where this wire is slightly faster. Or yeah, there's some errors, with the other wire. Then what you would have is where, of course, well, the bits here are going to be arriving faster, which means obviously, well, they're going to get out of sync, and then you'll have a situation where, I don't know, maybe like let's say bit 6 here arrives right at the same time that bit 5 from this one arrives, and of course, yeah, then the data gets out of sync, right, it's skewed, yeah, which is going to cause obviously all kinds of problems. Right, and then I think the next one we can say, right, so if we said it's skewed, I think we can also talk about, well, serial has no crosstalk or no interference. right, no interference slash crosstalk. And again, the reason you get interference with parallel is because if you have, well, obviously, let's say on this wire you've got like an electrical signal. Obviously, right, this wire again, you've got another electrical signal. And of course, these electrical signals, if the wires are not insulated properly, those electrical signals can, interfere with each other. Right, so no interference slash crosstalk, or let's say hence, right, less chance of data corruption. Right, and then give one drawback of using serial half-duplex. So I mean, let's say, well, the speed will be slower. Right, speed will be slower. Yeah, let's say, right, than parallel. Yeah, so I guess, I mean, that's the disadvantage of using serial, right? If we think a disadvantage of using half-duplex, and of course we don't need to say that because we only need one. But if we did, we can say, well, obviously the data can only be sent in one direction at the same time. So it means you wouldn't be able to upload files to the server, right, and download files from the server at the same time, which of course in reality would actually be, quite annoying, to be honest. Right, D, the company uses a proxy server to help protect the web server and the network from cybersecurity threats. Give 3 cybersecurity threats that the proxy server can help protect against. Right, so I think, I mean, the obvious one, well, DDoS, right, distributed denial of service attack. Yeah, or just denial of service attack. And then, yeah, let's just put in brackets, right, DDoS. And of course, the way it can do this is because it can look at the IP address of the request, and if it sees one IP address, requesting like thousands of resources per second, well, then it can just block that IP address, because obviously well, let's say a legitimate user is not going to be making like thousands of requests per second. Right, so I mean, the other ones you can just say some more general things. Maybe you can say like a virus. Yeah, or I think a virus is maybe not the best one. I mean, we could say not adware, maybe like spyware. Because, for example, and I mean, obviously, well, spyware, this is obviously a type of hacking. But let's say, I don't know, they have a database, or they have, some customer details or something, right, on their server. Well, someone might want to install spyware on that server, in order to, let's say, yeah, I guess, well, in order to obviously access the database, right, in order to, download those customer details effectively. Right, and I guess another one, you can list another type of malware, so you could say, well, yeah, I mean, you could say like ransomware, they want to, yeah, hold the server to ransom. But I think rather than say malware, let's say something else, right, so we could say brute force. And this would be a brute force, probably trying to brute force their password, their username. I mean, it could also be brute force, I don't know, like looking for files, right, trying loads of different file paths, for example. But yeah, I think, right, just saying brute force, right, that should be okay. And of course, again, the way that works is, well, it's just going to be based on the IP. So if the proxy sees like one IP address making like thousands of requests per second, well, of course, then it's just going to block that IP. Right, identify 2 functions of the proxy server that can be used to help protect the web server and the network. Okay, so we could say maybe it will act as a firewall. So right, act as a firewall and can be used to block requests based on their IP address. Right, block requests based on IP address. Right, and I would also say like maybe privacy or privacy, because if you have a proxy server, that means that the hackers or whoever, they're going to see the IP address of the proxy server, right? They won't see the IP address of the actual final web server. So yeah, I think we can probably say that. Right, so yeah, let's say hacker, right, can only see, right, IP, or let's say, yeah, IP address right, of proxy server. And then, yeah, let's say, right, not web server. Right, next one, customers access the company's web pages that are stored on the web server. Describe how the web pages are located, retrieved, and displayed on a customer's computer. Right, so in here we've also got three parts, right, located, retrieved, and displayed. So I think when they're talking about located, really they're talking about DNS. So how do we, yeah, I guess how does the customer, type in the actual domain name? Yeah, how does that get converted into the IP? In order to know like which web server to actually go to. I mean, retrieved, maybe this is saying, well, obviously the web server has to find the file on its own system, based on the file path, for example. And then displayed, I guess this is talking about the web browser, taking, let's say, the HTML, right, but I mean also the JavaScript, the CSS. I mean, let's just say taking the HTML code, right, and then obviously rendering that on the page, right, displaying it to the user. Yeah, so I mean, I think let's have a quick recap of DNS. Right, maybe here. So what's going to happen then is, right, let's say here we've got the client, right, the user. So right, I mean, let's say they're going to ask, and in fact, right, maybe let's not do that, because I mean, really, there's multiple steps, right? Like, okay, let's say we're trying to find the IP address of, I don't know, Google. So first, and I don't know, I mean, let's imagine we're using like Google Chrome or Firefox. So, I mean, first Chrome will actually look, I mean, does it know the IP address of google.com? Because basically the browser will store that IP address, for like, for a given time. And I think the time is actually not long, right? Just 1 or 2 minutes. And the reason for that is because, well, if you get like an invalid DNS request, maybe it's been maliciously modified, you wouldn't want to be using that malicious like IP address, for like a day or a week, right? That's why they only store it for like 1 minute. But anyway, yeah, so first it's going to check, right, does the browser know the IP address? Right, if the browser doesn't know, then it's going to ask the operating system. And for example, the operating system is actually going to be in the host file, and yeah, you can search like host file, Windows, host file, right, Mac, Linux, and yeah, you can actually have a look at this yourself. Right, so yeah, again, first it's going to ask the browser, then it's going to ask the operating system. All right, then it's going to ask the, I mean, I guess you say DNS server, but basically it's going to be the router, because the router will have a built-in, DNS server. Of course, if the router knows, it's going to respond with the IP address, right? If the router doesn't know, right, then it will go to the ISP. And of course, if, the ISP, right, the internet service provider. And then, yeah, if the ISP doesn't know, then it's going to go to like the global DNS servers, right? It's going to ask them. And of course, eventually, well, hopefully someone will know. And then, yeah, whatever server knows is going to, just like respond with that result back at each stage. Each stage is then going to cache the result, right? So it's going to save it temporarily. And then, of course, when it then gets the IP address, let's say, yeah, 200, right, dot, something, something, something. Of course, then the web browser can make a request to that IP address. Yeah, that's obviously going to reach the web server. Because, of course, it's going to, travel like via the routers. So, yeah, maybe it goes to this router, then this router, finally the web server. Of course, the web server then responds, right, with the HTML code. And then, yeah, I guess that HTML code, again, is going to get rendered by the browser. Yeah, so that should be fine. And I guess here on the server you could mention the server might have to do some processing. Maybe it has to look up some database query. It has to find some file on its system, and then of course once it's done all the processing, once it's generated the code, yeah, then of course it can send that code back to the client. Right. So I mean that's basically what we want to explain. So I think here I'm just going to keep it shorter. I'm going to do bullet points, although in the exam, like, definitely write in full sentences. So what we can say is, I mean, let's say I don't know, maybe user, or let's say user enters, and what is going to be domain name, or let's say URL. Yeah, I guess URL into browser. Right. I guess we say what the DNS request made. Right, DNS request made to, I guess to convert domain name into IP address. Right, and I mean here we can say it's hierarchical. Yeah, that's a word they often use. I mean, like mainly for A level, to be honest, but you can also use it for IG. And the reason we say it's hierarchical is, yeah, I mean, how to write this? Let's say maybe hierarchical request. Yeah, I know which. Let's say which first checks browser, right? Then OS, right? Then, yeah, then let's say routers DNS server. Right, so first checks. Yeah, let's go browser. Right then OS operating system. Right, let's say yeah routers DNS. Right then let's say ISPs DNS. And I mean honestly, you probably don't need this much detail, right? ISPs DNS. Right then let's say right then finally. I mean let's say the global, right, or it's also called like authoritative name servers. So these authoritative name servers, yeah, these are like the global ones. Or let's say, yeah, maybe I know any device, or yeah, anything. Let's say any device. Right, that knows. Or we could say, let's say the first. Right, first device that knows IP address. Right, for, yeah, this domain. Right, yeah, will respond. Alright, let's say yeah, and yeah, IP will be cached at the sort of like lower stages. Right, yeah, cached at lower stages. Right, so at this point then we can say the browser, right, browser makes request to this IP address. Or yeah, we can say what makes, yeah, okay, I mean since it's web pages, right, let's say makes HTTP. Again, let's put in brackets, like maybe HTTPS. Right, request, yeah, to this IP. Right, and we can probably say request routed by routers. Or yeah, maybe request, maybe like traverses network. So traverses just means like travels across. Right, so traverses network, let's say via routers. Right, and arrives at web server. Well, I mean, hopefully arrives at the web server, right, if there's no errors. Right, web server. Yeah, and I think, I mean, I've done too much detail here. You can, and I mean, also the other thing, writing with this tablet, right, the handwriting becomes huge. So I think, yeah, like if I was writing with pen, we can probably fit all this in. And that's the thing with these 6-mark questions, right? I think some people, like, maybe they would only write, I don't know, maybe they only write, this many lines. But when it's 6 marks, I mean, really, you want to make sure to at least write, the whole thing. And to be honest, like, even if you write more, that's also, yeah, that's also good. Because here, I mean, they're really looking for detail and, keywords. Right, so I guess, well, it's arrived at the web server. Then we can say web server processes request. Let's go, right, web as web server. Right, processes request. And we could give an example, right, e.g., I know, finds file. I don't know, maybe, yeah, like DB request, right, database request. Yeah, maybe it's going to execute some code. So it could be like some PHP code or some JavaScript code. Yeah, any like server-side code. Right, and let's say right then, yeah, then returns HTML. Or yeah, not I, right, HTML code, right, to user. Or yeah, I guess, well, to user, to client. And to be honest, not only is it going to be HTML, it's also going to be the JavaScript, the CSS, right? It's going to be any like images, audio, video. Yeah, obviously all of the files on that page. Yeah, so you could say, I don't know, like HTML code and resources. That should also be fine. Right, okay, yeah, to client. Let's say, right, the browser. Let's say, right, browser then, let's say renders code and resources. renders code, yeah, and resources, yeah, to display to user, right, to, yeah, DS display, right, to user. Yeah, I mean, so hopefully that should be enough for 6 marks. Number 8, it says a student has a computer as a central processing unit, CPU, and we want to describe the role of the CPU in the computer. So if we think, I mean, the CPU, well, it's just going to fetch, decode, execute the instructions. All right, so yeah, probably we can say, I think, yeah, will perform the will perform the fetch, decode, execute cycle. Right, fetch, decode, execute cycle. Yeah, let's say what, to continuously execute instructions. Right, yeah, to continuously execute instructions, you know, while instructions are available. Yeah, while instructions are available. And to be honest, I think even while instructions are not available, it's still kind of doing an instruction. It's just doing like a no operation instruction. Yeah, so I think hopefully that's enough for 2 marks. Right, the CPU contains registers. State the purpose of a register. So a register, think well like the program counter, you know, the accumulator, yeah, the MAR, MDR, CIR, things like the status registers. Right, so we say, well, the registers, they're going to be, well, small fast access memory inside the CPU. So let's say small temporary, right, fast access memory. And I mean, yeah, fast access, this is the main one. Right, inside the CPU. And you know, obviously, well, I guess the most important thing is that it's fast access, because I mean, otherwise you'd either have to go to the cache, you know, and I mean the cache is relatively fast, but of course not as fast as the actual registers. Yeah, or then even slower, you'd then have to go to RAM. And again, I guess, yeah, worst of all, you have to go to secondary storage, right, which is like super slow. So that's why here, you know, you have the registers inside the CPU, and because there's like the small physical distance, you know, and because I guess just the way they're made, you know, they're sort of advanced electronics, right? They're going to be fast. Yeah, that obviously means that, you know, the instructions can execute quicker. And I guess we could mention what they store. So let's say to store, let's say instructions and data. Yeah, I suppose, well, instructions, addresses, and data. Yeah, okay, right, instructions, addresses, and data. I think I won't write that. Right, give 3 registers that are built into the CPU. So again, like we said, well, the PC, and let's just write what this is. So program counter. Alright, yeah, it's kind of difficult to write with this tablet. Like, honestly, going off topic, but this pen is kind of really stupid. You know, they've got buttons exactly where you put your hand. So whenever you're writing, you know, you're just accidentally clicking these buttons to like erase and things. Right, so let's go MAR. Right, that's going to be the memory address register. And then I mean here, I guess we can just go MDR. Right, yeah, MDR. Right, so again, well, memory, right, that's going to be, well, data, and then obviously register. And you know, if you want other ones, of course, you can go CIR, right, the current instruction register. I think for IG, I mean, yeah, maybe status register they might not accept for IG. So I think, you know, just go with these. And then, yeah, I mean, if you wanted, you could say accumulator, but I think, yeah, go with these 4 should be okay. Right, one component in the CPU is the arithmetic logic unit. Describe the purpose of the ALU. Right, so again, I'm just going to do bullet points, but yeah, in the exam, you know, write whole sentences. So we see, well, it's going to, let's say, execute or perform. Right, execute, let's say, arithmetic, well, yeah, arithmetic, right, and logic instructions. Right, let's say, for example, yeah, and let's go arithmetic. So that's going to be what? Addition, right, subtraction, let's go multiplication, and I guess, yeah, division. Yeah, I suppose they would be the main arithmetic. And let's go logic. So we can go what and. Yeah, let's go what not. Yeah, well maybe and or. You know, of course we can go XOR like this. Right, they would be some of the main ones. Yeah, I think that's okay. You know, you can also mention that maybe the result is passed to the accumulator. Yeah, well, result passed or copied, right, to accumulator. Alright, yeah, that should be enough. Alright, no, okay, I thought it was the last question, but seemingly not. Right, the student wants to replace the CPU to increase the performance of the computer. Explain why a different CPU can increase the performance. Right, so for these, I think they have three ways to increase the performance. Right, one is going to be increasing the cache. Right, another is going to be clock speed. And then I guess, yeah, hang on, my mind has gone blank. Right, so you can increase the cache, you can increase the clock speed. Right, yeah, and you can also increase the number of cores. So, I mean, yeah, let's, yeah, I don't know, I think maybe we don't need to draw this. So, I mean, the cores, let's try to explain, so, well, yeah, right, increase cores. Or, yeah, increase number of cores. And, you know, the way that works is because, well, let's say here, this is our processor. Now, if our processor only has one core, right, then we can only execute one instruction simultaneously. But let's say we have like a quad-core processor. So here our processor has 4 cores, right, and then each core is going to have its own, you know, probe counter, MAR, MDR, CIR, you know, accumulator, right, ALU, right. So it's going to have all, let's say, control unit, right. It's going to have all of those components, yeah, inside each core. So what that means is if we've got 4 cores, of course, we can simultaneously execute 4 different instructions. So let's just write that, right. Increasing cores, yeah, means we can. Yeah, I know, simultaneously, right, execute right, multiple instructions. Yeah, that should be fine. So, you know, we can run multiple processes at the same time. Right, if we're increasing the amount of cache, so and again, you know, some cache can be inside the core, right, some cache will be shared between cores, and then I think you'd also have some cache like outside of the CPU. But, you know, what cache is useful, I mean, similar to registers really, and it's just going to be, let's say, fast access memory that's close to the CPU, you know, or in some cases, right, inside the CPU, right, inside the cores. And I mean, the reason that's going to speed up is because, well, you can store more data and more instructions inside the cache, right, rather than having to go, let's say, to RAM each time. So, of course, yes, storing data closer to the CPU, right, that's going to be faster. So here, let's say, yeah, increase cache. Let's say cache capacity. Right, capacity, right, that's going to mean, yeah, let's say, well, more instructions and data. Right, more instructions and data, right, can be accessed quickly. Right, quickly, yeah, without, right, without having to go to RAM. Right, let's just explain that, right, which is slower. Alright, so yeah, hopefully that makes sense. And then what if we just want the clock speed? So again, what increase clock speed. And I mean, yeah, the way this will increase the performance is that, well, on each tick of the clock, right, one instruction is executed. Or you can say, you know, one cycle of the fetch-decode-execute cycle completes. Yeah, and I mean, like, it's not going to be the whole thing, right? It's not going to be like the fetch, decode, and execute cycle happens in one cycle. I think in reality it should actually take 5 because, well, I mean, really the fetch stage actually takes 2. I guess the decode stage will take 1, right, and then the execute will also take 2. I mean, this is at least according to the A-level book. But yeah, you don't really have to worry about that. But I think what you can say is, you can say, well, you know, one stage of the fetch, decode, execute cycle can occur, right? Therefore, let's say if this is our clock speed here, right? Let's say this is a slow clock speed of, well, when I say slow, let's say like, I don't know, you know, 1 gigahertz, or yeah, maybe even like megahertz. Whereas, you know, let's say we have a clock speed of like 3 gigahertz, yeah, something like that. Then of course, well here this means that we're executing 3 times more instructions, because again on each, let's say on each pulse of the clock, yeah, let's just say that, right? So increased clock speed means, well yeah, means faster CPU. Right, well let's say yeah, because right on each, let's say on each pulse or tick, yeah, okay, pulse, right, PLSE, yeah, okay, right, on each pulse slash tick, right, let's say yeah, one stage, right, of, and again, write this in full, right, fetch-decode-execute cycle, right, will occur. Yeah, I mean, I'm not sure if that's enough. You probably want to say hence. Yeah, hence, more clock cycles mean more fetch-decode-execute cycles happen per unit time. Yeah, you'd probably want to be a little bit more detailed. Alright, anyway, so the last question. A printer runs out of ink and needs a new ink cartridge. An interrupt is sent and a message is generated to notify the user that the ink cartridge is empty. Right, complete the paragraph about the use of an interrupt in this process. Use terms from the list. Some of the terms in the list will not be used. You should only use a term once. Right, so we've got, well, binary, then clock. And again, with these questions, right, make sure to read all the terms first. Right, so yeah, binary, clock, computer, data error, right, fetch code, execute cycle, hexadecimal, higher, interrupt queue, right, interrupt service routine or ISR. Right, then lower, printer, priority level, secondary storage, sorting, and transmission. Right, so I mean, let's just think how this works. Yeah, I'll try and draw it here. So what you're going to have, let's say you got, I don't know, process A, this is executing. So of course when I say execute, I mean, the fetch decode execute cycle is happening. Right, then let's say we've got this interrupt. I mean, well, let's just call it B, or maybe let's call it P, right, the printer. So this is when the printer is out of ink. So the printer, well, and let's say, yeah, this is when the interrupt occurs. So the printer sends this interrupt, right, to the CPU. So what's going to happen is, well, the register contents of, this A process, they're then going to be saved onto the stack, right, or we say saved into RAM. And when I say the register contents, I mean, the values of the PC, the MAR, the MDR, CIR, right, etc., status registers. Right, all of these contents are saved into RAM, right, or saved onto the stack. And the reason it's saved is because, well, when we, sort of say resume execution, right, we're going to want to reload these values. But anyway, what's going to happen there? So when we're here, right, the printer causes the interrupt. So now what's going to happen is, well, this printer has a interrupt service routine, and this interrupt service routine, again, it's just going to be code in memory. And of course, because it's code in memory, well, it's going to have a memory address. So what happens is the memory address of this ISR, so I mean, let's just do that, right? The memory address of the ISR, let's say it's like 100. This is loaded into the PC, right, the program counter. So now the program counter has the memory address 100. Of course, as the CPU executes, well, the CPU is then going to, well, obviously it's going to, load this into the MAR. It's then going to fetch the instruction at memory address 100, right, load that into the MDR. Yeah, it's going to copy that. It's going to copy that instruction from the MDR into the CIR. Yeah, during the decode stage, well, the control unit is going to decode it. Right, then it's going to be executed. So effectively we're saying, well, this ISR is code, right, and of course, yeah, this is just going to execute. So let's just draw this as executing here. All right, when it gets to the end, well, when it gets to the end, right, I mean, that's when we can actually load A back in. So yeah, that's when we're doing this one, right, we're loading back the contents of the PC, right, the MAR, MDR, CIR. Of course, loading all this back in, and then, A can just continue executing from the point it was at. And I suppose actually to give more detail, what we say, when an interrupt occurs, right, there's also going to be an interrupt queue. So let's say we have, I don't know, like interrupt 1, yeah, maybe interrupt 2. Now let's say interrupt 2 has a priority of like 5, whereas, and I think, in reality actually it's the opposite, where like a low priority, or okay, well, let's say a lower number means a higher priority. So an interrupt priority of 1 is, let's say, the most important, or yeah, maybe 0. Whereas let's say an interrupt priority of 5 is, less important. But so what we would say then is, well, because this one has a high priority, of course this one is going to execute first. When this interrupt is finished executing, right, well then it's going to check the interrupt queue again, of course, if there's another interrupt in here, right, well then that's going to execute. Of course, when the interrupt queue is empty, well that's when it can then reload this process A, and obviously continue executing this process A. Okay, so I think that's what we want to sort of fill in the blanks on this thing. Right, first one then, the something sends an interrupt to the something. So I guess the thing that's sending an interrupt, well, that's going to be the printer. And I think with these, you also want to check, well, is there any other like suitable answer? So binary, no, right, clock, computer, no. So I think printer here is the only kind of reasonable answer. Right, then that's, you can say, well, that's going to send an interrupt to the CPU. However, CPU they actually don't have here. So I think, the sort of reasonable answer is then going to be the computer. Right, the interrupt is given a something. Right, so the interrupt is given a priority level. I'm just actually going to do an arrow. Right, the processor completes its current something, right, and checks the something to see if there's an interrupt with a something priority with the current task. So what we said, well, the processor will complete basically the current instruction. So the current instruction, I think that's going to be this fetch-decode-execute cycle. Right, and checks the something. So well, it's going to check the interrupt priority. So where do they have that? Okay, alright, so I guess, we're not really checking the interrupt priority, right? We're checking the interrupt queue. We're checking the interrupt queue to see if there's an interrupt with a higher priority than the current task. Right, so if there is, it stores the current task, so that's what we said, it's going to store, the register values of the current task, and fetches the interrupt. So when it says fetches, I think here, right, so it then calls the, this is what it's fetched, right, it's the interrupt service routine, right, the ISR, which is a sequence of instructions that handles the interrupt. The interrupt is handled, which generates a message to the user to notify them that the ink cartridge is empty. This one is quite, I guess, quite difficult for 7 marks. Like if you know it, I guess you can say it's, maybe quite an easy 7 marks. But I mean, if you've got no idea about interrupts, then honestly, there's a lot of people that will probably just be getting, 0, maybe 1, 2. That's where you need to know in, quite a lot of detail. Right, so I think the last one, handling interrupts, is 1 functions of an operating system. Give 2 functions of an operating system that relate to memory. Okay, so I mean, you can talk about like memory management. Memory management, obviously you don't have to write this, but that's going to include things like paging. Right, it's also going to be, virtual memory. And then, I guess you say sort of paging / segmentation. So I mean, what paging is that's just, you say, it's going to break down the RAM into, let's say into fixed size pages. And usually, I think on Windows, these pages are like 4 kibibytes. Maybe it depends on your specific, your specific, machine. But I think on mine it's 4, I don't know, maybe kibi or kilobytes, right? Probably kibibytes. So paging is just going to be what breaks RAM into those individual pages. And then, let's say when you want to like load in a page, well, of course you load in 4 kibibytes. When you want to, move out a page, of course you move out 4 kibibytes. Segmentation is similar, although the pages, I guess not the pages, the segments wouldn't be fixed size. Although actually paging is mostly what's used because, it's going to be more efficient, and there's like various other advantages. Right then, virtual memory, I mean, hopefully people remember, that's where if the RAM is full, then you can actually use the secondary storage as, sort of extra, let's say extra kind of temporary RAM. And, you take things from RAM, right, you can put it in the virtual memory, of course, temporarily while you don't need it. And then, when you need it again, of course, you load it back in. Right, so you're paging in, paging out. You can also call that, right, swap, so swapping in, swapping out. And this here, this is also the swap space or swap disk. This secondary storage is, again, the swap space or swap disk. Right, so I mean the next one is a bit difficult. So honestly, I did check the marking for this, and they just say multitasking. I mean, I was thinking they might accept something like scheduling, because I mean scheduling is actually multitasking. It's the same thing, really. Because again, if you've got like two processes, well, you can't have one process that uses all the memory. Obviously the operating system has to allocate memory fairly. And again, the way it can do this is by using, virtual memory, by using paging. I guess using algorithms to make sure there's, a fair allocation of memory. But anyway, guys, I think that's everything. So hopefully this video was useful, and if it is, then see you again in the next video.